Okay, concept F is going to continue what we started yesterday. Yesterday we looked at nonpolar and polar bonds. Today we're going to focus on how those contribute to the polarity of an entire molecule. So molecular polarity is not the same as bond polarity. However, we can't do molecular polarity without bond polarity. So what we talked about yesterday was a bond between two specific nonmetal atoms, and their polarity was dependent on their electronegativity difference. Today, when we look at molecular polarity, we're talking about the entire molecule. So how do all the different types of bonds in the molecule contribute to its polarity? So this depends on electronegativity difference between all the atoms that are bonded together, and then it also depends on the shape and symmetry of the entire molecule. Alright, so we're first going to look at polar molecules. Now, in order to be a polar molecule, the following criteria have to be met, both A and B. There has to be bonds that are polar. So we're looking at the polar bonds, are they greater than a 0.4 electronegativity difference? And they have to have a shape that doesn't cancel out. So this is considered an asymmetrical shape, or will sometimes be referred to as a mirror test when we take a look at them. One thing I'm going to point out in the next couple of slides, because this is a really important term, or phrase I should say, is that polar molecules have an uneven charge distribution. Because we have these polar bonds and it's asymmetrical, the charge, or the electrons, are distributed unevenly throughout the molecule, creating that polar molecule. Alright, so our first example, we have carbon bonded to 3 hydrogens and 1 chlorine. Now, the CH bond, which is a 0.4 electronegativity difference, are nonpolar. However, there is one polar bond between the carbon and the chlorine, which gives you a 0.6. So we see that this creates poles between carbon and chlorine, and there's nothing to cancel out that pull of electrons towards chlorine. You can see that shown as a vector here with the arrow pointing towards the more electronegative chlorine. So we have a polar bond that's present, and we can see that it has an asymmetrical shape. It doesn't pass the mirror test, is what we like to call it. And really we're looking for multiple lines of symmetry. If it can have more than just one line, then that means that we have a symmetrical shape. And I'll show you a couple examples of that tomorrow. And then once again, because these two criteria are met, we have an uneven charge distribution, and thus we have a polar molecule. Alright, now we have HCl. So the HCl bond is 1.0, so we do have a polar bond. You can see the charge distribution here. Chlorine is more electronegative, so the vector is pointing towards it because that's the pull of the electrons. It does have a polar bond, and it's asymmetrical. It doesn't pass the mirror test in multiple planes. So we do have an uneven charge distribution, and thus a polar molecule. Finally, for our polar molecules, we have ammonia, NH3. The difference between N and H is 0.8, so we do have 3 polar bonds. However, the shape is asymmetrical, so it doesn't pass more than one line of symmetry. So thus, we have a polar bond, and it's asymmetrical. So we can see with these that we have nitrogen, which gets that partial negative, and then 3 hydrogens become partially positive. You can see the vectors drawn here towards the nitrogen. So we would have a high density of electrons around the nitrogen. So thus, this polar bond and its asymmetrical shape give us an uneven charge distribution and is thus a polar molecule. So you can see here, the red is where the electrons are spending their time around oxygen. This is an example of water. And we can see where these hydrogens are, we get a partially positive charge. So this creates an uneven charge distribution, which we want to know this because when we talk later about intermolecular forces, this can change different properties of substances and that type of thing. So it will come up later on as well, and we'll apply it. All right, moving on to our nonpolar molecules. We have to make sure that in order for it to be a nonpolar molecule, either A or B has to be true. Either all the bonds are nonpolar, so they all have an electronegativity difference of 0 and 0.4 to 0.4, or it can have polar bonds, but it has a shape that cancels out these polar bonds. So we say that it's a symmetrical shape, or it passes the mirror test where it has multiple lines of symmetry. Now, nonpolar molecules have an even charge distribution. The electrons are evenly spending their time around all the atoms in the molecule. So our nonpolar molecule examples, we have methane, which is CH4. All of the bonds between carbon and hydrogen, those bonds are all 0.4. So we have all nonpolar bonds, so criteria A is met. So we have an even charge distribution and thus a nonpolar molecule. All right, we have carbon dioxide on our left-hand side. In this case, we have a 0.8 difference in electronegativity, so we do have polar bonds. There's two of them, and you can see by the vectors they're both heading out to oxygen. So they actually cancel each other out, which we can also refer to them as being symmetrical. I have multiple lines of symmetry in CO2. So this is an example of having polar bonds, but they're being a symmetrical shape. Also, CCl4, we have a similar scenario. All the bonds between carbon and chlorine are 0.6, so they're all polar bonds. However, this has a symmetrical shape. So all those polar bonds cancel each other out, so we still have an even distribution of charge around the molecule. So in both cases, we have polar bonds. However, they're symmetrical, so it meets criteria B that we outlined 2 slides ago. So we have an even charge distribution, and thus both of these are nonpolar molecules. All right, so a nonpolar molecule has an even distribution of charge between the atoms, either between 2, 3, 4, and so on. We would all get the same picture where they're evenly distributed around the molecule. Okay, that's it for concept F. We're going to work a lot with this because it's going to really tie into a couple of other topics later in this unit and some other ones that we do following it.